Yeah, can everyone see the screen?
Yeah.
Okay. Um,
Yeah, I can give a introduction maybe.
sure.
So this is a project to design and build a new zkVM, and the main goal here is compatibility with existing code, with things like Rust or anything that compiles to LLVM. There will be a compiler from LLVM to this zkVM bytecode, and we want to make it really as efficient as possible so that it's not just a theoretical possibility, but it's becomes really practical to take something like geth and compile it to zkVM and prove its execution with little or no changes to geth itself, just as an example. So it's a little bit uh, maybe comparable goals to something like RISC-0, but a different approach, because this is not sticking to a conventional ISA like RISC-V. This is departing from convention and coming up with a new ISA that's a little bit more snark friendly. So for example, there's no need to parse a kind of bit-oriented instruction format, and there's no need to support things like 32 registers, which don't really make sense from a cost perspective in a zk setting. Max, do you want to go over some of the in some more detail?
Yeah, I mean, I guess we can start by maybe just talking about the high level architecture. So I think in addition to like the goals that Daniel stated, we also want to have this VM be easily extendable. So we want kind of a core, very simple instruction set, and then have the ability for like an arbitrary number of additional instructions to be added for, field arithmetic or elliptic curve operations or hash functions. We don't want to try to predict in advance kind of what the functionality that everyone will need. So we kind of have an architecture in which there are multiple tables, multiple starts. There's a core CPU trace that has sort of a memory buses to each of these other tables. So one of these is a memory, basically memory table, read-write memory. We have 3 buses going to that table that supports 2 reads and 1 write in a given in one cycle of the main CPU. And also a kind of pager table that the memory can read from. This can be useful for things like continuations, which we can kind of discuss later. I think as also part of the core configuration or core instruction set, we're kind of baking in a start friendly hash function, tip 5, and yeah, I mean, the idea is that like depending on what program you want to compile, you'd sort of add, U32 arithmetic, or maybe down the line will also support 64-bit arithmetic. But yeah, these are basically all of these tables. These are just some examples or sort of optional. Yeah, Daniel, I don't know if you wanted to add anything there. Otherwise, I can talk about the instruction format.
Yeah, please go ahead.
Okay. Yeah, so I think Daniel mentioned we're not really doing any bit packing in our instructions. We just kind of have this very naive but simple to decode format where there's 6 field elements. So like the first element represents the instruction, and then 3 elements for the operands and 2 kind of indicating whether there are immediates present in the operands. Yeah, we also, so we do have actually two types of memory. We have a read-only program memory that the program counter points to. This is likely just going to be done with a kind of preprocessed lookup table. I think, yeah, memory, like we're trying to sort of not have any weird memory addressing models. Like our memory will be sort of word aligned. So we'll assume that we're always kind of reading a 32-bit word for now, and basically 4 field elements. Like normally one field element will correspond to 1 byte. I think this will differ if you're using a field arithmetic coprocessor, but otherwise you can sort of assume that 1 field element corresponds to 1 byte. So yeah, immediate values, we don't need to touch on that. Yeah, as Daniel mentioned, we don't have any general purpose registers. We're sort of more closer to something like Cairo. Cairo supports like 4 memory accesses per CPU cycle. We just, I mean, we think that general purpose registers sort of only strictly add overhead. And because memory is pretty cheap, it's not necessary. We also don't have a dedicated stack. We just operate directly on the like call frame in memory. Yeah, I guess before I move on, did you have anything else to add, Daniel?
Maybe one thing worth mentioning is that, like Max mentioned, the program is pre-processed. We basically take the program and build a lookup table from it. And one implication of that is that we don't really support dynamic programs. So for something like if there was a blockchain using this VM bytecode where the bytecode was kind of like the user supplied arbitrary bytecode and it wasn't known until runtime, that's not something we're looking to support at the moment. At the moment, we're looking to support use cases where there's one static program. So it in some ways it's a little bit more restrictive, but there are a lot of advantages to doing it this way. I think it's more efficient. We can just load code with lookups without touching memory, and also it's also if we can make assumptions like if we can treat the code as trusted or the compiler as trusted, then that just simplifies a lot of things and makes a lot of things more efficient. For example, if we do something like division by 0, we don't have to prove that a fault occurred. We can just, it doesn't really matter what we do because it's undefined behavior.
Can I ask, what specifically in a blockchain setting, which types of programs would the restricting to static programs exclude? Would something like a constant function market maker be out of the picture?
Would it be a static program, or what would that look like?
Well, I'm just like, which are the dynamic programs normally used in a setting that we would want to use for blockchains, which we couldn't with this?
So for example, in our like Polygon zkVM, we take some dynamic program code at runtime and we load it into memory while also computing the hash of it. And then from that hash, we can take that hash and prove that this is the correct program code as it exists in Ethereum state trie. So that's the sort of use case that we're not trying to support right now. Does that make
Right, so
sense?
it doesn't, yeah. So it doesn't exclude, say, specific applications, any application in particular. Okay, well, thanks.
Yeah, so I guess maybe next we can just talk about some of the instructions that we've been kind of thinking of adding here. So I think, yeah, within the core instruction, we only have we only kind of have loads and stores and jump and like a subset of jumps available, or like the instructions that you would need to execute something like call. I think we don't want to make assumptions on really anything outside of that, and just let these other instructions, including 32-bit arithmetic, kind of be optional. So we have we have like a load 32 instruction that is basically like, so all these operands are relative to a frame pointer. Like an operand is either basically an offset value relative to this frame pointer or an immediate value. And so load and store are basically like following the pointer to this offset value. And then, yeah, I mean, writing or reading from, basically writing from another offset. And stores kind of doing the opposite. We also, we need a way to sort of load in values, I mean, basically set memory to begin with. And so we have a couple instructions that this is like store the first two elements of a given word, or store the last two elements of a given word from immediate values that are passed in as operands. And I think, these jump and link variable instructions are essentially implementing this, I mean, calls within our VM. So it's updating the program counter and updating essentially the frame pointer. Should also mention that we've been collaborating with Wei Dai on this, and he's made a lot of contributions here. I mean, I think that's mainly, we do have like a simple jump here, but I think, we have some other types of jumps and another optional configuration. I don't need to go into too much detail maybe on what these do. I mean, we just have field arithmetic instructions. These operate again on not like the whole word, not like the whole 4 elements, but just the first element in a word. We have like instructions to and from field elements to convert this to a 32-bit value that we can then do comparison checks on.
Just one question.
Sure.
So what does checked addition and checked multiplication do on overflow?
The idea is it would just compare. We're still working through, exactly whether these are really necessary, but the idea is that it would just check like that the overflowing bytes are basically 0.
Okay, but would it fail the proof or would it jump somewhere else?
Yeah, that's still
Okay.
an open question. My
Okay,
idea was that it would just be unsatisfiable, but we're kind of wondering whether we even need these instructions in the first place, or it can just be handled yeah, with the other instructions.
Okay, thanks.
Yeah, and I think at some point we will want to add byte manipulation instructions. So these might be helpful for things like RLP decoding or right, a block header like serialization or deserialization. But I think for now, we're just going to assume that things are word aligned and basically use shifts and bit mass to kind of implement these sort of things, which I think will add some overhead, but we just want to see kind of what the performance is to begin with. Yeah, Daniel, I don't know, maybe you want to talk about heap, stack versus heap idea there.
Yeah, so I think we're only going to have one address space. It'll be kind of a conventional addressing system where the heap grows from address 0 upwards and the stack grows from 4 gigabytes downwards. So no virtual memory, none of that stuff. And one bit of an open question for us is how to implement malloc, but what we're thinking right now is we initially will have a very simple malloc that just never reuses addresses. So free will be a no-op. Malloc will just increment some pointer to the next unused address. This would mean that basically we can't use more than one program can't allocate more than 4 gigabytes total since it's a 32-bit machine. So that might not work for all use cases, but I think this could at least be a useful option if somebody is never going to use more than 4 gigabytes. And if they'd like a really fast malloc, then that seems ideal. Yeah, and then I think it's kind of an interesting open question of if that doesn't work, then what's the best way to do memory allocation in zk? Like, there's probably some non-deterministic tricks we can use to help with the to help with determining which memory segments are available and that sort of thing, but haven't really thought through that problem yet.
Yeah, I guess, so I mentioned before, we just have like a single, I mean, we really only have 2 registers, like a frame pointer and program counter, are basically all variables, like the arguments to a call, and then the local variables within a call frame are just relative to this frame pointer. Frame pointer is always pointing to the return address. The local variables are below the frame pointer and the arguments and return value are above. I think an important kind of note here is that we don't like, this kind of constrains us to only have static, basically statically sized allocations on the stack. We don't support dynamic allocations on the stack. Instead, we store those in the heap, and you'd have to, for now, use load and store instructions to sort of pull those values back into the stack frame. And I think it's sort of an open question about whether this needs to be optimized further. Like, a few different directions we could go to do that would be adding additional about adding additional buses to memory, so that we can operate, directly on heap values instead of doing this indirection. But yeah, we're just not sure whether it's really necessary for most programs. But yeah, I think we're leaving that kind of door open and just implementing this to start with.
Yeah, so right now it's basically a RISC style architecture where accessing memory goes through load and store all the time, unless it's a local variable, and then we can directly access it. But anything on the heap goes through load and store. And yeah, we're debating if it's best to stick with that simple model or maybe add some features like, in x86 you can directly do addition or other operations on values in memory.
Yeah, so yeah, I mean, we're just trying to kind of work through some simple programs to make sure that kind of there aren't any edge cases that we haven't identified here. But yeah, we're working in parallel, sort of writing the LLVM backend to try to get some simple programs compiling. But yeah, I mean, maybe I can skip to just the design notes. I don't know how useful it'll be to go through the trace. It's also like we don't have the constraints kind of written down at the moment because we've kind of continued to iterate on the instructions, and I'm not sure that they're actually that complicated to write down. But yeah, maybe Daniel, you can talk about like the backend that we plan to use and some of the differences maybe compared to other VMs in the moment.
Yeah, so this will be built on Plunky 3 backend. So Plunky 3 is going to be a kind of a very modular toolkit for polynomial IOPs, a little bit like ArcWorks, but more focused on performance. And yeah, it will have this kind of multi-Stark approach where we can have a main Stark for the CPU and other so-called coprocessors for things like caching, memory, etc. And we don't have the prover working end-to-end yet, but we're really optimistic about the performance. We're using this smaller Mersenne field where arithmetic is very, very fast, and we have a lot of optimizations planned for how to do things like memory efficient FFTs.
But you're going with, so you said Stark, so it's going to be air and not Plonkish arithmetization for the VM, right?
Yeah, exactly.
Yeah, I think we touched on this earlier, but the memory will basically be in a separate table here. So for each CPU instruction that accesses memory, there are basically 3 rows that are going to be added to that trace, the memory trace. And I think all coprocessors, so most coprocessors won't be directly interfacing with memory. They'll be interfacing with the CPU trace, and the idea is we'll just be able to sort of load an instruction right from the read-only memory and kind of pass that, basically fetch the appropriate, operand values from the operand offsets, and then kind of pass all that information along to a coprocessor. So yeah, I mean, there's not a ton of kind of overhead here. I think one of the reasons why we don't want to bake kind of memory into the main trace is that we do want to, I think, support this continuation kind of idea where instead of proving the execution of instead of having a single proof for the entire program execution, you kind of split it up into smaller batches of execution cycles and have some mechanism of kind of independently proving these, but serializing and deserializing the memory needed to do so kind of between between consecutive batches. So I think that that's probably easier if we have a separate memory table and we want to kind of pursue something that's more efficient than just basically Merkle tree deserialization, essentially. Yeah, maybe Daniel, you can well explain that.
Yeah, I was going to say the other nice thing about having memory in a separate table is it means that we can have these shared memory coprocessors. So for example, if we want to accelerate Ketchek, of course we can have a coprocessor that just does one permutation that's always supported. But with memory being a separate table, we could also have a coprocessor that does an entire variable length hash, reading the input from memory, and then finally producing the output. Or just as another example, if we wanted to accelerate memcopy, we could just have a very simple coprocessor that, reads 1 byte from memory, writes 1 byte, decrements the length, and just kind of simulates that memcopy loop in hardware. And Plonky theory should support this in a very efficient way. So each coprocessor is like its own Stark, but they can be committed to in parallel, and they can share the same Merkle tree. Even if these Starks have different lengths, we can still put all of the trace data in a single Merkle tree and share authentication paths. And then when we run Fry to verify openings, it's for the entire set of Starks. They all get merged together into a single Fry instance. So there shouldn't be much overhead to adding additional coprocessors.
Do you think it would be possible for so you have all of these tables and they result in different witness polynomials. I'm not sure about the permutation check, but maybe it would be possible to, instead of committing to all of them separately, having just a random linear combination of them and doing something with that. Well, it might not work because of the constraints. Yeah, I don't think it would work.
Yeah, I think we need the original values for the constraints, but
yeah.
What we do is when we are doing the commit phase of Fry, we start with a kind of a special step where there's no folding, or we could think of it as like a 1x fold, so there's no compression. So if we had a higher fold in the initial step, then that would mean all of these original polynomials would have to get opened at multiple points, at not just the point being queried, but also neighboring points. But when we start with this special fold, this special 1x fold, then they only get opened once per query.
Yeah, I guess I'm not sure what else we should touch on.
I have some questions on the instruction set.
Sure.
I
Yep.
may. So I'm wondering, aren't you missing shifts and maybe some more conditional branches?
Yeah, I think.
Or is it just
the-
not too fixed yet, the instruction set?
Yeah, we definitely are missing some. I think the other conditional jumps and like branching logic, I did have a separate kind of table here, and I think it's been commented out. But yeah, the bitwise instructions, like, I think should be able to take care of masking. You were talking about branching and then, oh, shifting, yeah. So shift, maybe Daniel can jump in. I don't know kind of the most efficient way to implement that.
Yeah, me too. In the Polygon zkVM, it's done with multiplication and division, but by a power of 2. But yeah, there's some other techniques for it, and I'm not sure which one's going to be best. Oh, there's a question.
Yeah, Thor. So I guess why, yeah, why is the VM not register or stack based? So yeah, I mean, I can attempt to answer that, and Daniel can follow up. I mean, I think for registers, like it's sort of only adds overhead in a sense, like right, registers in conventional architectures are there because memory access is like expensive and has some latency associated with it. So if we remove registers, we basically save on columns or just trace cells that actually have to represent the register values. And we also save on just unnecessary instructions that are sort of dealing with register assignment. And yeah, I think both of those, we don't know like how substantial, I guess, the performance will be, like performance improvement will be without them, but they are kind of just unnecessary. And I think for stack, yeah, I mean, Daniel maybe can answer this better, but I think just empirically, there's kind of work that shows the stack-based architectures kind of have performance overhead compared to register-based ones. I mean, it depends on the program that you're talking about. Like, don't think that's always the case, but I think on average, it just kind of adds overhead. And again, like if we're just operating directly in memory, there's and memory is cheap enough, there's kind of no reason to have this dedicated stack.
Yeah, I would just add, I think one of the main differences between kind of the conventional physical world of ISAs is that here there's no latency considerations. So for memory access, we get the result immediately. Conventionally, even if it hits L1, then it's a few cycles. And for that reason, it's like not just a matter of cost, but a matter of latency, why registers are conventionally useful. And I think even if we have a sort of page miss and have to load this memory data using Merkle proofs, it's still available immediately in the same cycle. So yeah, I think that's probably the number one kind of difference in the cost model that we have.
Hey guys, I had a quick question. Maybe there's something I'm missing here. My understanding right now is this instruction set is essentially like an LLVM backend, right? So you can compile more traditional programs into this LLVM backend and then into circuits or into a proving system. The field element instructions, like when would those be used from the higher level language, like the from and to and the field element add sub?
Yeah, it would be used if you're doing really any like native field arithmetic like operations in your code, like native here being like in the same, this 31-bit field, which yeah, I didn't touch on this, but you'd have to do a little bit, like we don't expect that there's going to be just an immediate kind of plug and play code reuse. You are going to have to import some custom libraries like to support kind of field arithmetic. But those should really just consist of sort of inline, like a inline never code where we can basically just pick out the function identifiers and substitute like the body with our instruction. So it should still be performant on like, whatever native like machine you're running the code on. It's not that you kind of have to use some suboptimal instruction set to be able to prove it on RVM. But yeah, like most people probably not be doing, maybe outside of like, I guess if you're doing like in VM recursion, that's like an example where you'd want yeah, native field arithmetic support that's optimized. But yeah, we expect that most people will just use like non-native field arithmetic coprocessors that can just be added as needed. Does that answer your question?
Yeah, that does make sense. So you potentially in the high level language would have an SDK that is much more efficient if it uses these instructions than traditional instructions.
Yeah, exactly. And the hope is that like that SDK is literally just kind of like a normal library, like maybe the existing field arithmetic library that people, whatever people are using in their programs, but just with kind of flags that have been passed or decorators essentially on functions that sort of prevent that code from being kind of lowered prematurely in LLVM.
Cool. Thanks for explaining.
Yeah, but that is one area where that's like a big motivation for trying to get this kind of proof of concept LLVM backend working, because it would be nice to be able to demonstrate that that's feasible and not a headache for developers. But
we could also try to use these field arithmetic instructions just to replace U32 operations when we can. So for example, if you just have a simple loop that loops up to 100, then in principle, it would be easy to replace that with things like, add one field element and then do an equality check with field elements, which is also cheap. Not sure if it's really worth optimizing that sort of thing because U32 math isn't that expensive either, but yeah, just something to consider.
yeah, are there other questions? Daniel, is there anything else that maybe we should talk about? Or
I think we covered everything for now, but if anyone's interested in collaborating on this, please get in touch. And yeah, definitely eager to get some more hands and to make this more of a community project.
yeah,
It should be fully open source. The whole stack should be, I think, probably MIT licensed.
How far is your LLVM backend?
I've been working on it for the past couple weeks, I think. So I have kind of all the boilerplate code in place, and I have kind of basic call frame, like, you know, formal argument lowering and kind of return value lowering. The major task right now is just the instruction selection, which, I mean, we don't have that many instructions. It shouldn't be. We also don't have, you know, we just for now have one instruction format. So yeah, it's, I mean, I think it's feasible within the next week. I'll have some like prototype that can do just basic like addition and multiplication and hopefully like a Fibonacci program. But yeah, I think it might be a little while until we have like a feature parity with, you know, the other backends and can be able to support any code. But yeah, it's not actually that bad. I mean, there's a learning curve, but one of the newer frameworks in LLVM, this like global instruction selection framework, actually like greatly simplifies a lot of the kind of tasks and has pretty good kind of defaults. So yeah, I'm planning to like just work a little bit more on that and then open that up. And yeah, if anyone is like has interest in contributing to that, like I'd be happy to collaborate. Like Daniel said, like everything here is going to be fully open source, like no code obfuscation, like MIT license. So yeah, it's yeah, if you're interested in helping out, like yeah, I'd love to collaborate.
Okay, great. So I'm just asking, so this looks very suitable for what I'm doing with Powder. So as soon as you have some working examples, I would very much like to modify the front as so that they fit together.